Okay, so welcome to the 8th lecture of data mining at Google. The relevant points up here to you are basically that we're going to finish up chapter 6 today, which is on the association rules, which we started last time. So you don't care about the midterm there is another homework posted, but I will mention to you we probably won't meet next Friday, but I'll give you details about that and I'll send that around on the email. So chapter 6 was association analysis. We started it off last time with some definitions. Basically, the classic data set for the association analysis is the supermarket data, and you have, for each transaction, you know what people bought. And sometimes, if they're using like a club card, like a Safeway, that you know actually for each customer what they bought. But in this case, it's actually transactions, and you're looking for strong associations. So association analysis uses a set of transactions to score rules, indicate likely occurrence of an item based on the occurrences of other items. So if I bought diapers, am I likely to buy beer? If I bought milk and bread, am I likely to buy eggs and Coke, etc. And we talked about the fact that implication means co-occurrence, of course, not causality. Item set, a collection of one or more items. The key thing there is one or more items. We're not going to consider the empty set as being an item set. The support count, basically how often does that item set occur in absolute terms. So milk, bread, diaper is in the last two, so its support count is 2, but its support is 2 out of 5 because 2 out of the 5 transactions contain milk, bread, diaper. And then frequent item set, basically that's going through all the item sets which have a sufficiently large support and pulling those out. So the min support is your minimum support threshold. Okay, so association rule, what is it? It's an implication expression of the form X implies Y, where both X and Y are item sets. So for example, milk diaper implies beer. Milk diaper is an item set, beer is an item set, and the association rule is milk diaper implies beer. Now one thing that this doesn't say is, but it's sort of, you wouldn't put anything on the left also on the right. You wouldn't say milk diaper implies milk beer. That sort of wouldn't be adding any extra information. So generally the two item sets on either side are disjoint. Okay, the two main definitions, because these are the two main metrics we're going to be using, are the support and the confidence. And I'll talk at the end of today about some other measures that may be more meaningful depending on what you're trying to do. But the book spends most of chapter 6 talking about this problem formulation using support and confidence. So we'll talk about what those are. Support is simply the fraction of transactions that contain both X and Y. So we defined before the support for an item set. This is the support for an association rule. Is basically if you have the association rule, for example, milk diaper implies beer, the support for that association rule is the support for the item set containing both sides. Okay, so the support of milk diaper beer basically is the support for milk diaper beer. Okay, so milk diaper implies beer, support is the support for milk diaper beer, and again there's 2 out of 5. So the support for this association rule is 2 out of 5. What does that mean? It means that 2/5 of the transactions contain milk diaper and beer. Then the confidence basically is the strength of the association, whereas the support is the frequency. Confidence measures how often item sets in Y appear in transactions that contain X, right? So for milk diaper beer, the confidence is out of all the transactions that contain milk and diaper, how many of them also contain beer? So if you like the probability, someone mentioned last time, isn't this just conditional probability? Yes, it is. This is the probability of this is the probability of beer given milk and diaper. So out of all the people that bought milk and diaper, how many people also bought beer? Well, 2 out of 3. Two-thirds. Two-thirds of the transactions that contained milk diaper also contained beer, so that's what we call the confidence. Okay, so these two rules, or these two definitions, support and confidence, are the main metrics that we're going to be using, and at the end of the day I'll talk about some limitations on these. So I think this was the first example that we started doing last time. It says, compute the support for item sets A, B, D, and ABD. So, and it says to use the transactions. Notice we have the transactions and we have the customer ID here. We're just going to begin by using the transactions, and of course these numbers are all unique, so we have 10 unique transactions. So let's see, support for A would just be 1, 2, 3, 4, 5, 6, 7, and so I'll call that the support of A is 7 out of 10. 7 out of the 10 transactions contain A. Support for the next one is BD. That one is how many contain both B and D. That's just 1, 2, 2. Only 2 of them actually have both B and D. Okay, so that's 2 out of 10. And then the support for ABD. And as you're doing this, you should sort of think about algorithms, right? I know that this one has to be a subset of this one. So I really don't need to look at all of them anymore. I just have to look at those two that contain B and D and see how many of those contain A. And that would be, so let's see, here's the one that's BD. That does contain A. The other BD doesn't. So this support is just 1 out of 10. And so that problem is done, which is number 26. Any questions on that one? Okay, so those are the support for those 3 item sets. Now, moving on to association rules, this one asks you for the confidence for the association rules. BD implies A, and A implies BD. Now notice I didn't ask for the support for these 2 rules, but the support for these 2 rules would be, of course, 1 out of 10, right? Because you would just look at the support of A, BD. But the confidence for these rules, let's see, that one, number 27. Let's see, confidence for, let's do the first one, BD implies A. So basically this is asking, out of all the transactions that contained B and D, how many also contained A? So on the top, I want to put basically the support of A, B, D, and on the bottom I want to put the support for B and D, right? Out of all those that contain B and D, how many also contained A? And so the top here is 1 out of 10, and then the bottom here is the BD 2 out of 10. So this rule, we would say, has confidence 50%, right? 0.5, 1/2. So half of the transactions that contain BD also contain A. That's what's called the confidence of the association rule. And then the other one, just to show you, of course, it's not symmetric, would be the as for the confidence for A implies BD, right? Out of all the transactions containing A, how many also contain B and D? Well, the numerator is still the same, right? A, B, D goes on top. However, the denominator now is everyone who got A, right? So numerator is still 1 out of 10 here, but the denominator now becomes, whatever, 7 out of 10. So this rule has much smaller confidence, right? Numerator is still 1 out of 10. The denominator is now 7 out of 10. And so this rule has confidence only 1/7. So you're not very confident in this, right? Only 1/7 of the people that bought A also bought both B and D. So this is sort of a low confidence rule. So you can't, if someone bought A, it's not very likely that they also bought B and D. Okay, any questions on that? Again, it's just a conditional probability calculation. I think the interesting thing is that sort of this is the problem formulation, because we're going to talk about problems and difficulties with formulating the problem in this way. When I say this way, I mean looking for rules with high support and high confidence, and I'll explain that more in a second. The other thing you might want to do with this type of data, we're doing this at the transaction level. If you do have people with membership cards, you can track the same people over multiple transactions. And of course, you can imagine analogies of this to sort of other applications, but if I give everyone an ID card when they buy something, I know who they are, and in this case I actually know the first 2 transactions belong to customer 1, the next 2 transactions belong to customer 2, et cetera, et cetera, et cetera. So I have actually 5 unique customers. So I might not want to think, it depends on what I'm trying to do. If I'm trying to sort of group products together on the shelves, I might be interested in doing things at the transaction level. But if I'm trying to cater to certain customers, right, maybe I want to open a store that caters to a certain type of customer, then I might be interested in looking at things at the customer level. And that's what the next question asks. It says, compute these things treating each customer ID as a market basket. So then you can sort of collapse your table into, what is this, number 28? You can collapse it into customer ID. And there's 5 customers, 1, 2, 3, 4, 5, and you can write down what each customer bought. And I'm gonna, so the first guy bought everything, right, at some point, A, B, C, D, E. So he bought everything, and we're not really keeping track of how much of each product they bought, just whether or not they bought it, just a binary thing. Next guy has also bought everything, A, B, C, D, E, okay? But number 3, looks like he did not buy A, right? Number 3 came a couple times and he never bought A, but he bought everything else. So he bought B, C, D, and E. Customer 4, he did buy everything except E. A, B, C, D. And then customer 5 bought everything except C. A, B, D, E. So let me put these little placeholders there to indicate where they didn't buy something. Okay, so that's the same data at the customer level. And so now, of course, we can compute support at that level. Support of A, well, everyone but one person bought A, so that's 4 out of 5 people bought A. Support for BD, well, let's see. Everyone bought BD, it turns out, right? There's no B is missing, no D is missing, so that's 5 out of 5. And then support for ABD, well, actually, I think from these two, you can actually infer this one, right? If everyone bought B and D, the support for ABD has to be the same as the support for A, which is 4 out of 5. Okay. So that's the same calculation, only now we've collapsed it and done it at the customer level, which may be more interesting to you if you're talking about not sort of stocking the shelves for each transaction, but opening a store to cater to certain customers. Okay, and then finally, we can do, using the customer ID as the market basket, we can also do the strength and confidence for the association rules. And let's just see, this is number 29. Okay, so the confidence for, which one is first? BD implies A. I'll mention to you that, the notation here and the notation in the book is sort of sloppy. So, sometimes I'll write set notation, sometimes I won't. But this is the confidence for BD implies A. So on top, I put, the ABD triple, which is 4 out of 5. And on the bottom, I put everyone who got B and D, which is 5 out of 5. So this one comes out to be 0.8 or 4/5. So 4/5 of the people, before it was of the transactions. Now 4/5 of the people who bought B and D also bought A. Well, who bought B and D? That's everyone, and then 4/5 of the people bought A. So that rule has confidence 0.8. And then going the other way, A implies BD. Okay, so on the top, that's got to be, again, the 4/5, the ABD, the support for the ABD triple. On the bottom, I'm going to put everyone who bought A. Well, that's the support of A, 4 out of 5. So this rule actually has 100% confidence, right? 1.0. Everyone who bought A also bought B and D, right? Who's everyone who bought A? It's these 4 people, and they also bought B and D. But everyone bought B and D, so that actually doesn't really tell you anything interesting, right? The confidence of that rule, A implies BD is 100%, but anything implies BD is going to be 100% because everyone bought BD. And we'll sort of talk about this as being a limit to confidence. It's not a relative measure, it's an absolute measure. But it is true, right? If someone bought A, then I know for sure they bought B and D. But nothing special about A in that context. Okay, any questions on that? Question?
As a practical matter, do people ever look at sets with like not A?
Yeah, so I think that's the real thing, and I'll talk about that in a second. If you're going to talk about the confidence of A implies BD, you really want to compare it to the confidence of not A implies BD, right? You really want to get that relative comparison. And I think that's one thing that's sort of missing from this treatment, and we'll talk about it. I mean, you could say, okay, let me look at confidence of A implies BD, and then compare that to everything else implies BD. But if A is sort of a majority thing and everything else is a minority thing, that can be misleading. So I think that as a rule of thumb, if I'm going to sort of formulate this problem, I'm going to do it symmetrically. And if I'm going to look at A implies something, I want to know the confidence for not A implies the same thing and compare the relative terms. Now, I'll do an example of that in a second. Okay, other questions on these calculations or this problem? Okay, so let me give you sort of a more realistic example. This one is from the Stats 202 logs, and we can pick on the Yahoo crawler, who sort of tells me that they visited by leaving me this string in my logs, which actually has, I think has like the help page where you can read about, why are you crawling my site and things like that. And the question is, what is the confidence for the rule the Yahoo crawler implies this IP address? Right? Does the Yahoo crawler always use this IP address, or do they, sometimes use different IP addresses when they visit my log, right? So the question is, given it's the Yahoo crawler visiting my logs, what's the probability that it's this IP address? And so we can take a look at that. Let me find these web logs again. Let's see, I think it's more Stats 202 logs right here. So open with Microsoft Excel. And I do this text to columns, and oops, you have to click on the column, I guess. Okay, There we go. Data, text to columns. Delimited by the space will do the trick. Okay. And all I really care about right now is the IP address, which is the first column, and then this last column, which if you sort of ever look at your web logs, most of the time is uninformative. It just sort of tells you the browser type. But when it's a crawler, the crawler is usually nice enough to sort of identify themselves. So like, let's see, here's some examples. I don't really know. These are probably just individuals with using that type of browser. But even actually the first observation here is the Yahoo China crawler, right? Slurp. And there's a web page you can go and read about who they are. And usually on that web page, of course, they'll tell you why they're crawling your site and how to make them stop and things like that. So that's the China crawler from Yahoo. I'm actually going to look for the US one, which we'll find. And then you can see there's other companies sort of that have crawlers that crawl your web pages. Let's see, the MSN crawler is in here in some places. I think I saw him before. Anyway, all these different crawlers. Oh, here's the MSN crawler, right? MSN bot. Okay, but what I'm interested in is when the Yahoo crawler comes, is he always coming from the same IP address, or does he mix it up? And the main question is, what is the frequency of that IP address, given it's the Yahoo crawler? So I'm going to do the pivot table again. Let me just insert rows. This is IP. Oops, that's IP, and I'll put that this is who. Before I make the pivot table, I will mention one relevant number is that there's 14,083 rows, 14,803 rows, right? The first row I put the column titles, so total number of rows is 14,803. So that's going to be involved in this calculation for the support and confidence. 14,803 rows. Just remember that. Okay. Now let's see. I want to count up how many times the Yahoo crawler is using that IP address. So I'm going to do data, pivot table, and pivot chart report. Let's see. Next, first two columns here. Let's see. I want to put actually first who and then IP. Right, because I want to have IP nested within who. And then I'm going to put count of IP here. And that should do the trick. And this is sort of messy here with the low screen resolution, but let me hide some stuff and make some stuff bigger, and you might be able to see it a little better. So here I have who, and here I have the IP. And if you sort of look through the who, let me make the who a little bit bigger. So the first one is who has not identified themselves. Then here's Mozilla 4.0, here's the 5.0's coming, and let's see, this one might be him. Nope, that's not him. Let's see, what was it? Mozilla 5.0, how does it read? It's alphabetical, right? Mozilla compatible is the next word, so I need to go up to compatible. I got compatible. Yahoo Slurp, so that would be Y, that would be down. Okay, there's the Google bot. Okay, let's see. Go down some more for Yahoo. There he is. There's the Yahoo crawler crawling my page. Okay, so you see right away, in fact, he's not always using the same IP address. He's using all these different IP addresses here. And the one that I was interested in was 74.6.19.105, 74.6.19.105. There it is, 31. Okay, so let's see. He's coming 31 times, and the other relevant number, so let me write down 31 so I don't forget. The other relevant number is the total number of times the Yahoo crawler is showing up in here. And the pivot table gives you the totals down at the bottom, and that's 714. Those are the three relevant numbers I need for that question. And so now we can answer it. It says, support and confidence for that rule, right? So let's see. I don't have my calculator, I'll just use R. Okay, so we want Yahoo crawler implies that IP address. So the support has to be all the times that I have the Yahoo crawler and that IP address, which is the 31 out of the 14803, right? That's the support. And I think this comes out to be about 0.2%. You can check that. The confidence is going to be, out of all the times where it's the Yahoo crawler, how many times is it that IP address? So that's 31. So you see these guys always have the same numerator, but the support is relative to everyone. The confidence is relative to it being the left side, right? If it's the Yahoo crawler, what's the chance it's that IP address? And I think this comes out to be like 4%. Let me check those two numbers, otherwise I'll get emails from all over the world telling me I don't know how to do division. So let's see, what is that? 31 divided by 14803 is roughly 0.2%, and then the other one was 31 divided by 714 is like 4.3%, so we'll call it 4%. Okay, so that answers the question, and so what can we say? We can say, well, only, 0.2% of my records have the Yahoo crawler and that IP address, so it sort of has small support. But once I know it's the Yahoo crawler, there's a 4% chance that it's coming from that IP address. So that's the confidence for that rule. Now, I can ask you, too, the opposite one, right? If I said, what is the support and confidence for this IP address implies the Yahoo crawler, well, of course, it's going to have the same support, because support is symmetric with respect to the association rule, so that would be still 0.2%. But what do you suppose is the confidence for the other direction? 100%, right? If you look at this IP address, every time you get that IP address, it's going to be the Yahoo crawler, because, no one else is using that IP address. And the easy way to do that would be make the pivot table, but nest the other one inside that, and you'd see it right away. And so if you were doing a predictive task, right, that would be sort of really easy to predict that it's the Yahoo crawler if you know the IP address, because there's sort of a one-to-one mapping right there. Sorry, not one-to-one mapping, but a direct mapping. Okay, so I think that's all I wanted to say about this. Any questions on this problem? Okay, so thinking about sort of these weblogs and this exercise, you might think, well, I picked out a specific association rule and asked you to compute the support and confidence for that. But that's not how you would do data mining. You wouldn't say, hey, I wonder if, this is interesting, and then figure out the support and confidence for that, right? Because how are you going to know what's going to be interesting? There's so many association rules that you can make from your data that you don't want to have to figure out the interesting ones. The data mining task is for you to sort of run an algorithm over the whole data set, consider all possible rules, and return to you which ones are interesting, or in this case, which ones have high support and high confidence. And that's sort of the formulation that your book talks about for the problem, right? So this is an association rule data mining task, the following. Given a set of transactions, so you can think about supermarket data, you could think about weblogs, whatever you want to think about, find all the rules, and this all is a big number, right? There's a lot of rules. Even with a small supermarket data set, you'll see there's a lot of rules possible. Having the support exceeding some minimum threshold and the confidence exceeding some minimum threshold. That's the data mining task. That's the formulation of the problem that the book talks about in sections 1, section 2, section 3, et cetera, et cetera. They sort of focus on this one specific formulation of the problem, which, as I said, we're going to talk about today, has a lot of limitations, but a lot of people have worked on algorithms trying to solve this problem. Okay, find me all rules, all possible rules having a support above a minimum threshold and a confidence above a minimum threshold. And so here you say, well, what would be the brute force approach? What rule are we trying to improve on? Now, this is really naive, and you'll see that you would never do it. But the most naive thing would be list all possible association rules. Okay, there's way too many of them, but you could list them all. Compute the support and confidence for each rule. Okay, a lot of computation. And then, remove all the rules that don't meet both of these criteria. Okay, of course, the problem is it's computationally prohibitive, and not only that, it's pretty stupid, because you can see there's a lot of shortcuts right away. The first thing that you notice is that you can decouple the support and confidence requirements. Because whenever you calculate support, the support of an association rule ignores the arrow and ignores what's on both sides, right? So, for example, all these rules involve milk, diaper, beer, right? Milk, diaper implies beer, milk, beer implies diaper, diaper, beer implies milk. All of these association rules are going to have the same support. They're all going to have support of 0.4, because for all of them, you're simply looking for milk, diaper, and beer. So you say milk, diaper, beer is there, milk, diaper, beer is there, and then it's not here. So all of these have support 2 out of 5 or 0.4. Doesn't matter where the arrow is, doesn't matter what's on what side. The way support is defined it's going to be the same for all of them. So this is sort of suggesting something already. You can sort of first do the support requirement, okay? Once you've sort of pulled out, item sets that have sufficient support, so example, milk, diaper, beer, then from those 3 items, you can start putting the arrow in and putting things on different sides and forming rules. And the rules, of course, will have different confidence, right? Like in the case of milk, beer implies diaper, well, wherever you see, I'm looking at these 2 things, wherever I see milk, beer, I also see diaper, right? If I see, let's see, no milk, beer, here's milk, beer, I also see diaper. Here's milk, beer, I also see diaper. Here's milk, but no beer. Okay, so that rule, 100% confidence. Some rules have small confidence. Milk implies diaper, beer, right? So milk is here, 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 and here, but how many of those also have diaper, beer? Well, this one and this one. So that's 2 out of 4.5, right? So they can all have different confidence, but they all have to have the same support if they're involving milk, diaper, and beer. So all these rules are binary partitions of the same item set, milk, diaper, beer. Rules coming from the same item set have identical support but different confidence. Thus, you can decouple the support and confidence requirements. So that's sort of the first thing you can do, and that suggests this 2-step approach, right? The first thing is basically don't look for association rules, just look for item sets. Just look for item sets who have support that's sufficiently large. Okay, not association rules, just item sets. Then from these item sets, generate rules by sort of, taking the binary partitions, by putting the arrow in different spots. And so first look at item sets that have sufficiently large support, and then from those item sets, generate rules by taking binary partitions. Now, step 1, find me all item sets who have sufficiently large support, is still a computationally difficult problem because there's a lot of item sets, okay? However, there's a lot in your text, and if you're an algorithm person, you might look through, like reading through that, about speeding up the computation of this algorithm using some creative ways of finding frequent item sets. But then that's step 1. Then once you have the frequent item sets, there's a lot fewer things left, and from those you can generate rules and calculate the confidence of those rules. So that's basically the problem formulation as given in your book. I'm going to do sort of one example of it. Yeah, I'm going to do one example of it to show you if we were just sort of going through, I don't want to say brute force because we'll be a little bit intelligent, but I'll just sort of show you how the problem goes. Question, Charles?
Do you start with all the one item sets?
Right.
Only if both of those items meet the threshold, then do you consider them
Exactly. So Charles's question is, should I start from the small to the big? And of course, that's what we're going to do. And so let's just sort of go through and do this one. So it says, use the 2-step approach to generate all rules having support at least 0.4 and confidence at least 0.6. So the question is, what item sets should we start with? Well, first of all, you don't need to look at the singletons, right? Because if you think about, well, if you're going to be sort of pragmatic about it, the definition of item set, so we go back to the definitions, right? Definition of item set has to be 1 or more items. Okay, that's the definition of item set. And then definition of association rule says X and Y have to be item sets. So I need at least 2 things, right? I can't make an association rule from one thing. So I'm going to first start with the doubles and look for all the doubles that have support greater than or equal to 0.4. And then I think what the point that's made is if from the doubles that have support greater than or equal to 0.4, then that will suggest triples, right? But a triple can't have support greater than or equal to 0.4 if it's not in some way represented by some of the doubles, and so on. Okay, so let's see. We want to find all rules having support greater than or equal to 0.4 for number 31, and I'm going to start with just item sets that have 2 elements. And so if I were to look through all possible pairs, you could write an algorithm to do that. Or if you just sort of want to do it by hand, I have.
You could start with the singlets first because then you can eliminate a lot that way.
Oh, I could eliminate single things that don't have. Yeah, that's true. I could. Let me see. Maybe I'll just do that. So, which singles can I eliminate? Anyone who doesn't occur at least 4 times, right? I can eliminate him. Are there any such ones though? I don't think there are. Oh, cookies. No more cookies. Okay, let's see if I can get rid of cookies then. That should speed things up. Get rid of cookies. Yeah, and then get rid of cookies. Let's see if this will work. Okay, so cookies do not exist anymore. Okay, so let's see. Then I basically just made a binary representation of what people bought here. And then I can just go through sort of the pairwise things, right? So take like beer, who's in column B2, and take his product with everything and sum him up. And what I would learn from that would be that, oh, I should mention an Excel technique here. When you put the dollar sign by either the column letter or the row number, that's an absolute reference. So see, the B doesn't change here when I go around. So I've taken the column B and taken its product with everything. Now B with itself is uninteresting, just tells me that the sum is 4. So 4 people bought beer, but I see 0 people bought beer and bread. 0 people bought beer and butter. 3 people bought beer and diapers, which is support point 3, which isn't big enough. And 1 person bought beer and milk, which is support point 1, which isn't big enough. So you could go through like this. I guess I only have a few columns. So let me take column C with everything. So this would be, and of course I am doing everything twice. I know that. So okay. So actually, this is interesting, right? Beer and bread. There's 5 people that bought both beer and bread. And there's also 5 people that bought both beer and butter. And is that true, or did I screw something up? It looks untrue. Bread. Oh, I did bread. I'm not doing beer anymore. I did bread. Okay, great. 5 people bought bread. Oh, that's not interesting. But 5 people bought both bread and butter. Okay, that sounds interesting. Bread and butter. So the support for the item set, not the association rule, but just the item set, bread and butter, is 0.5. And of course, well, butter, bread, same item set. So there is one. There is one that's a candidate. Okay, so I did beer, I did bread, I could do butter, which is in, let's see, column D. And let's see, that's going to tell me about butter. Oops. So I know this was 5 already. I know this is 5. 3 people bought butter and diapers, 3 people bought butter and milk. That's not interesting. Let's see. Then I do column E. Let's see here. Column E, and 7 people bought diapers, and there's 4 people that bought diapers and milk. Sorry, these aren't people, these are transactions. 4 transactions had diapers and milk. So there's another one that's above 0.4, right? Diapers and milk equals 0.4. And I'm probably done, right? I don't need to check the last column because I would have already done it with every other column. Okay, so that should be all pairs that I've looked at. And if I forgot any, I think I got them all. So bread, butter has support 0.5. Diapers, milk has support 0.4. So step 1 is sort of done. You've found all, well, hang on, I should say one more thing about it. But the pairs are all done. I'm trying to find all item sets that have support at least 0.4. Now at this point, I should ask myself, do I need to look further? Do I need to look at triples? And the answer is yes, no. No, I do not need to look at triples because if there were a triple, right, it would have to contain, either bread, butter, and something else, or milk, diapers, and something else. However, that something else would also have to be in a pair at least 0.4 times. So because bread, butter, and diapers, see, okay, if this was butter instead of diapers, it's possible that bread, butter, milk would be one. But because this pair is disjoint from this pair, there's no way, right? You can convince yourself there's no way it's going to happen because any triple would have to contain this double plus something else and this double plus something else. But this double plus something else, it wouldn't happen because then that other double I would have picked up as a unique double, and so can't happen. I'm done. Can't be 3. Has to be only 2 items, and so any association rules meeting the support requirement have to be binary partitions of one of these 2 rules. Okay, so that of course then suggests we look at the following 4 rules, which is bread implies butter. The other one, butter implies bread. Okay. Let's see, diapers implies milk and milk implies diapers. Diapers implies milk, and milk implies diapers. That's all that's left, right, from all the possible association rules initially. Okay, so let's see. Bread, butter implies milk. The top, I should have the support for if I bought both of them together. So let's just say BB. And on the bottom is, I know I bought bread, so the support for bread should be on the bottom. And if you look at this, right, turns out they're both 5 out of 10. It's hard to see here, but it's easier to see here that if you look at bread, 1, 2, 3, 4, 5 people bought bread. Butter, 1, 2, 3, 4, 5 people bought butter. They're identical. The bread and butter are identical in this data. So both of these are 5 out of 10. 5 people bought both bread and butter. 5 people bought bread. So this rule has confidence 100%. And then, of course, because I said they're identical, this one would be the same numerator, but on the bottom it would be the support for butter, which is also 5 out of 10. So this one is also 1.0. Okay, so both of those rules have 100% confidence, and they meet the support requirement of 0.4. So these two rules we found them, right? It's our data mining task. We found two strong associations in the data. If you buy bread, there's a 100% chance you buy butter. If you buy butter, there's a 100% chance you buy bread. And bread and butter co-occur at least 40% of the time, which was my minimum requirement. In fact, they co-occur 50% of the time. Okay, so that leaves us with the last two. Diapers, milk. Let me sort of fit it in over here. So let's see, I want to do confidence for diapers implies milk. Diapers implies milk. So on the top, I should have the support for diapers, milk. And on the bottom, I should have the support for diapers. Okay, so how many people bought both diapers and milk? Looks like 1, 2, 3, 4. And then how many people bought diapers? Looks like 7 people bought diapers. Okay, so this is 4 out of 7, which is what, like 0.56? So I think that doesn't meet my 60% confidence requirement. Is that right? 4 out of 7, 0.57, either way. Does not meet my 60%, right? 60% confidence. So this guy's out. So then there's only one last candidate to consider, which is the confidence for milk implies diapers. On the top of that one, I should have the double milk diapers, and the bottom I should have milk. Milk diapers is still 4 out of 10, but now milk, say how many people bought it? Milk should be 1, 2, 3, 4, 5 people bought milk. 5 out of 10, so this one does it, right? This is 0.8, which meets my 0.6 requirement. So my last rule is milk implies diapers. So those three work, that one doesn't. Okay, so this is sort of the data mining task that your book formulates in section 1. You throw the data set at it, you throw it the supermarket data, and you find an algorithm that says, give me all the rules that have support at least this much and confidence at least this much. And the two-step procedure is first look at item sets with that support and then form binary partitions of those to get the confidence. So if you read like the other sections in your book, they talk about sort of more efficient algorithms for sort of solving this problem. But you could see, just as we were going through it by hand, there's some obviously stupid things that you wouldn't do that would sort of save you some amount of time. And then there's sort of slightly more intelligent things that you can read about in the book in terms of how to save time, because the computational nature of this problem, when you say, give me all item sets that meet these criterion, that's a big problem just because there's a lot of item sets. Okay, any questions about anything that we just did? Okay, so the next thing to talk about is basically, even though your book spends all the time, well, most of the chapter on this problem formulation, which is give me all the rules that have a sufficiently large confidence and a sufficiently large support, there's some drawbacks to that. And the first thing, which I think we've sort of already noticed, is the fact that confidence is an absolute measure, right? So in this data set, and there's nothing like that's that special about this data set, but if you think about here, the confidence for tea implies coffee, right? Well, of the people that got tea, right, of these 20 people, 15 of them also bought coffee. So the confidence for tea implies coffee is 15 out of 20, 75%. And you say, if someone buys tea, there's a 75% chance that they're going to buy coffee. So, why don't everyone who buys tea, why don't I give them a coupon for coffee, or why don't I put the coffee right by the tea, or something like that, right? Because when someone's buying tea, I know that they're pretty likely to buy coffee. The problem, again, is that's an absolute measure. This 75% is not judged relative to something else. So what might you want to judge the 75% relative to? Well, you might want to judge it relative to the aggregate, right? 90% of the people in aggregate like coffee. So the fact that when someone likes tea, there's a 75% chance they like coffee. The 75% chance is actually less than the aggregate 90% chance. So liking tea actually makes you less likely, relatively, to like coffee, okay? You could also compare it to sort of not tea, right? Often when we put the bar over something, it means not. You could also compare it to not tea, which you know has to be higher if the aggregate is higher, right? Just has to be. So if you don't like tea, 75 out of 80 like coffee, right? So 75 out of 80 is 0.9375. So either way you look at it, whether you compare it to the aggregate or you compare it to the opposite, either way, liking tea has a negative association with liking coffee, right? Liking tea means you're less likely than aggregate to like coffee, or less likely than if you didn't like tea to like coffee. So the question is if you had the minimum support requirement. Right, right. So the question is, yeah, about that it has small support. The other thing that it sort of makes me wonder about with the support thing is the following. I mean, you could say, like, if I have this minimum support, minimum confidence thing, then, you know, if this one comes out to have sufficiently high confidence, then so is this one. So I should capture both of them. However, the thing that I worry about is suppose that it's not just like tea and not tea. It's tea and a whole bunch of other minority things. Then you might pull out this one, but something like, you know, some other strange drink might fall below your minimum support, and you might actually miss this. So I would be worried if you had any algorithm that turned up this one, but missed this one, because, you know, this is the one that has higher confidence. And so if I compute this one without comparing it to this one, I'm really doing myself a disservice. So that's sort of one of the drawbacks of confidence, is that it is an absolute measure and it's not a relative measure. Okay, and then there's a whole bunch of other problems along with it. Your book talks about, oh, sorry, any comments on this slide before I move to the next one? Okay, your book talks about a whole bunch of other proposed metrics. And if you notice, these are all formulated in probabilistic terms. And of course, you can formulate support and confidence in probabilistic terms, right? Confidence is simply the conditional probability of coffee given tea, and support, of course, is just the joint probability of coffee and tea. So thinking about probabilistic terms, there's a whole bunch of other ways to look for associations. And of course, you can design your own data mining tasks, right? You can say, give me all rules that have sufficiently large conviction, sufficiently large interest, sufficiently, you know, you can use all these different rules and design your own data mining task. And with each one of them, you know, it sort of leads to sort of algorithmic challenges to make the problem more tractable, because when you talk about all association rules, you're talking about a lot of possible rules. The book only focused, you know, really on support and confidence, so that they talk about some of these others, but with regard to algorithm, they really focus on the support and confidence. And here you see here again, the support is just the joint probability, and then the confidence is they actually write the maximum of the two conditional probabilities, just trying to make it symmetric, right? Basically, you'll pull up whichever rule, you'll pull up A and B if either one of the rules have sufficiently large confidence. So there's a whole bunch of other formulations that your book talks about. Okay, so I think that's really all I want to say about this sort of association rule data mining task for the most part. Your book talks about find me all rules with sufficiently large support and sufficiently large confidence, gives you a whole bunch of algorithms to solve them, then sort of talks about in section 6.7 that there are some drawbacks to that formulation, and mentions some of the other formulations. I think that's all I want to say about it. The last thing I want to talk about is what's called Simpson's paradox. Before I move to that, I'll just say, are there any comments on this? Okay, so I think I'm mostly, yeah, one question.
So how is the minimum threshold determined?
So,
Say that it's
you know,
sufficiently large.
yeah, so people will tune it, and, you know, and it's sort of a feedback loop. Am I getting out too many rules, you know, that really aren't interesting to me, or am I, you know, the opposite would be I'm missing some important rules. So I don't know of any formal way to set those thresholds.
So there could be like multiple iterations and then.
Yeah, you could say, oh, maybe I want to have, I didn't pull out enough rules. Maybe I want to pull out lower one of the two. The one thing I'll say about association analysis is it's simply a descriptive exercise, right? There's no real gold standard for it. It's just, am I going to learn some interesting rule from the data? So it's really exploratory. And so there's no like one formulation of the problem. There's no criterion for setting thresholds, things like that. It's really descriptive.
Has anyone done the work to evaluate these different metrics to see which ones tend to be most useful?
I think because this is something that it doesn't seem to be like so much an academia formulation of a problem as it does an industry formulation. I think there's some open research.
Are there standard data sets that people use for these?
I bet there's got to be one or two good supermarket data sets. I mean, I don't know, what's out there publicly, but it wouldn't be that hard, right, for them to put one out there. So I don't know of any sort of competitions or publicly available data sets. I haven't done too much work with association analysis, but I'm going to guess that there's, if you look at the book has a bibliography section too, and that might turn up some stuff for you.
I believe in Netflix.
Oh, yeah. Yeah, it's a big prize too, actually, and like $1 million or something like that. Yeah, so maybe we should all do that. Okay.
Actually, I looked into it. Google frowns on us doing stuff like that when Netflix is going to hold the results.
Oh, yeah. Okay. Probably I won't say anything more about that. Okay, so that's sort of association analysis. Now, the one thing you'll get yourself into trouble with, and I think I'll sort of reserve this to talk about sort of next time when we're sort of have our minds fresh, but we'll talk about what your book calls Simpson's paradox next time. And the problem with this is sort of it's the story. The short story is that when you look at things in the aggregate, it doesn't always tell the same story as when you look at things broken down by other variables. And so the first example I give is like a textbook problem, but then I sort of use the same numbers in a real context, and we can talk about sort of the implications of it. And it's interesting enough that I think I'll save it for next time. But I'll do the toy textbook example just now to get you thinking about it. So here's the toy textbook problem. The numbers are the same as my real problem, but it's just sort of a toy example. So a Simpson's paradox, and I don't even like the word paradox, which is why I quoted it, because I think as soon as you call it a paradox, you sort of marginalize it and sort of make it sort of a cute thing that might happen sometimes, but it's really part of a larger problem, which is whether or not you're going to control for sort of other variables. So it occurs when a third variable, right? So you're looking at the relationship between two variables, but there's some third variable, possibly hidden, possibly a variable that you haven't thought about or that you're not aware of, or maybe isn't even in your data, which would be really problematic. When this third variable causes the observed relationship between the two variables that you're looking at to disappear or reverse direction, or even, I mean, it could just weaken, okay? But generally, the paradox is when it disappears or reverses. But it's interesting to know if it weakens, are you interested in the weak relationship or the strong relationship when you don't consider it? So the example I'll give you is basically my friend and I are going to play a basketball game. Okay, now we're each going to shoot the same number of shots. I shoot 20 shots, he shoots 20 shots, right? I shoot 50%, he shoots 40%, right? 8 out of 20, 40%. So the question is, top level question, management level question, who is the better shooter? Me or my friend? And in aggregate, in the simplest story you can tell, obviously I am, right? Because I shot 50% and he shot 40%. Okay, now the thing is, who is the better shooter? This data suggests I am. Now suppose the management, they haven't really formulated their question that well. They said, who is the better shooter? But what they're really asking, and you kind of have to get this from them, they're not really saying who is the better shooter. They're saying, if I have to pick one of you two guys, so maybe it's a coach, right? I have to pick one of you two guys to go into the game and shoot the game-winning shot from 15 feet, who am I going to pick? And so you look at the data and you say, you pick me. I'm the better shooter. I shoot 50% based on this game. But you think about the real question. The question is like, if one person is going to go into the game to shoot a certain shot from 15 foot, right? We have a play that'll create an open 15-foot jump shot. Who should I put in? So the one thing that we should really be controlling for is distance of the shot, right? Because I know that the person that's going to go into the game, he isn't going to dribble around and throw up whatever shot he can get. He's going to go in the game, and we're going to run a play, and he's going to shoot a 15-foot shot. So if that's the real question isn't who is the better shooter. The real question is who is the better shooter when you control for the distance of the shot? Because I'm going to run a play to get an open 15-foot shot. Well, then I should control for the distance of the shot. So suppose I break the data down according to far shots and close shots. what can happen, right, if you look at me, right, so in aggregate, okay, I'll do the aggregate first. This is me, this is my friend. In aggregate, I am 50%, my friend is 40%. Okay, but if you break that down into, which way did I do, far and close, from far, I am 25%, and my friend is 33%. Okay, so he's actually better than me from far away. So you say, aha, okay, you must be better than him from close up. That must be what's going on. But from close up, I am 9 out of 16. God, I do all these fractions that I don't know what they equal. That's a problem. 9 out of 16. Thanks. I am 56% from close up. And he is actually 3 out of 5. He's actually 60% from close up. So this is the problem, right? He's better than me from far away, and he's better than me from close up. So no matter what play the coach is going to set up, I really want to put my friend into the game to shoot the shot. However, based on the aggregate data, it makes me look better. And so the problem is my friend isn't a worse shooter, he's a better shooter. He just was shooting further shots when we played the game. So if you control for the distance of the shot, my friend is better, but if you look in aggregate, you think I'm better. Now, again, if you did an experiment, right, an experiment would be carefully designed so that it's either randomized or controlled so that we all shoot the same type of shots. But remember, data mining is never experimental data. It's always observational. So this type of thing can sort of always bite you. Okay, when you're looking at the relationship between two variables, if there's something else that you should really be controlling for and you haven't, it can give you the exact wrong answer. And on the next time, I'll give you sort of a more practical example where this could come up. But if you think about really, the problem is that the question isn't well formulated, right? If you're going to put one person into the game to shoot a 15-foot shot, you don't say who is the better shooter. You say who is the better shooter when you control for the distance of the shot. Or if you're going to collect data, you know, in the data somehow you find some way to control for the distance of the shot. But if it's experimental, you at least, you know, at the very least have to measure it. Otherwise, it's gone and you can't even control for it. So this is sort of the textbook example of Simpson's paradox. I think you can sort of think about this. Next Tuesday, I'm going to give you sort of the same numbers, but put sort of a real story behind it. So just to give you a preview of what's going on next week, the class on campus has their midterm. So Tuesday, I'm going to review for them. For us, we'll sort of finish talking about Simpson's paradox, and I'll just sort of maybe go over some of the homework problems, and if there's anything interesting, I'll point out to you. But we'll probably meet for a short time Tuesday. Next Friday, we won't meet, and then we'll come back the following week, and we'll do classification and clustering to finish off the topics on the list of topics. Okay, any questions before we take off? Okay, great. I'll see you on Tuesday. One question.
Yes, so can we say that if we make the total number of shots for me and my friend?
Yes, yes. If you fixed.
At a granular level, let's say far and close.
Yes.
Then the paradox will go away.
Yes, exactly. We must control. That's one way we could control for it. Is we say you each have to take the same number of close shots. You each have to take the same number of far shots. Wouldn't be a problem. And if you're doing an experiment, you would do that in an experiment. The problem is with observational data, if you haven't even realized that the distance is variable and that it's a huge source of variability, you're really out of luck. And it really depends on how big of a source of variation it is. And here, whether the shot is far or close affects things a lot more than who's shooting it. So the biggest source of variability is the distance of the shot, not the person, which is why that's sort of overwhelming it and killing you. Okay, so we'll talk more about that next time. Okay, I'll see you guys on Tuesday. Have a good weekend.